Hello everyone and welcome to Introduction to Signal Processing with Wolfram U. This lesson is on modeling systems as differential equations. In this lesson, we look at two popular LTI systems and we model them as ordinary differential equations. Remember, by LTI we mean systems which are linear and time invariant. The two models that we will study are a series RC circuit and a unity gain Sallen-Key low-pass filter. A simple RC circuit consists of a resistor and a capacitor and a voltage source which are connected in a series or in a single loop. This is the most common circuit that you encounter in electrical engineering. Here we are not showing the voltage source and the voltage across the source is just called X of t. An RC circuit is an example of an LTI system with the input signal X of t, the voltage given by the voltage source in the circuit, and the output signal Y of t, that is here the voltage across the capacitor. Here we are interested in the voltage across the capacitor, and so we call that the output of the system. Recall that the current and the voltage for resistors and capacitors are related as shown in these two equations. Here IR and VR denote the current and the voltage for the resistor R, and IC and VC denote the current and the voltage for the capacitor C. Now to model this RC circuit mathematically, we apply Kirchhoff's circuit laws. First, applying Kirchhoff's current law to the node between the resistor and the capacitor with the directions that we have chosen for IR and IC, we get that the sum of currents leaving the node must be equal to 0, which is the sum of the currents entering the node. Now, substituting the current-voltage relations for each of these two components, we get one equation as shown here, which is a first-order differential equation. A first order since the highest derivative is first-order derivative. Applying Kirchhoff's voltage law, we get that the sum of voltages around the loop must be 0. This gives us two equations with two unknowns, VR and VC. And we are interested in VC, the output signal. So we solve the first equation for VR and replace VR in the second equation with its value from the first equation. And that gives us one equation in terms of VC, as indicated here. VC, the output signal of the system, we already called that Y of t. So replacing VC with Y and reordering the equation into the standard form for differential equations, we have this first-order differential equation with constant coefficients for this circuit. The constant RC here is called the time constant of the circuit. The goal in circuit analysis is to find the output signal Y of t, the voltage across the capacitor, in response to some given input signal X of t. We have modeled the system as a differential equation, and so to find the output signal Y of t, what we need is to solve the differential equation for Y of t. We will review later how we solve these differential equations, but for now, here, using the Wolfram language, you can see the output response of an LC circuit with time constant RC being equal to 1 second, when the input signal is a sinusoidal signal with angular frequency omega. The output, as you can see, is also sinusoidal. The fact that the output of a sinusoidal input is also sinusoidal, as we will show later in the course, is a fundamental property of LTI systems. Also, you can see that as the frequency of the input signal increases, the amplitude of the output signal decreases. This RC circuit shown here, in fact, is a realization of a so-called low-pass filter. We will discuss low-pass filters later in the course. As another example of modeling systems, let's look at the Sallen-Key circuit, which is a well-known realization of a so-called unity gain low-pass filter. In addition to the standard circuit components such as resistors and capacitors, it also incorporates an important electronic device called an operational amplifier or op-amp. Filters built with op-amps are called active filters, and those without op-amps, like the RC filter discussed earlier, are called passive filters. In this circuit, we have two resistors R1 and R2 and two capacitors C1 and C2. To get the equation for the circuit, we will start with the same voltage-current relations for each of the resistors and capacitors in the circuit. And if we label the currents as shown here and apply Kirchhoff's current laws, we get these two equations. The second equation assumes, as is common practice, that the op-amp is ideal with infinite input impedance and zero currents at the input terminals. Therefore, for the second node, we have only the sum of IR2 and IC2. Also, applying Kirchhoff's voltage law to each of the three loops in the circuit, we get three equations as indicated here. Vt, the node voltage, is labeled in the circuit. We can solve these equations now for VR1, Vc1, and VR2, and then get the currents of each element using the voltage-current relations. Replacing the current values in the first two equations, then we get these equations shown here. This way, we have modeled the Sallen-Key circuit as a system of two first-order differential equations, which we can solve to find the two unknowns, the node voltage Vt and the output voltage Yt. X of t is the input signal, and it is known. We could also solve here for Vt and then have one equation in terms of just Yt. This equation is a second-order differential equation, as indicated here, and it is second-order differential equation since we have the second derivative of y of t. Again, the coefficients are constant, and so we have a linear constant coefficient differential equation. The differential equation again can be solved for the output signal y of t using a well-known solution method that we'll discuss later. But for now, using the Wolfram language, we can get the output response of a Sallen-Key low-pass filter to sine waves as input signals with frequency omega for a range of frequencies of the input signals. As you can see, once again, the amplitude of the output signal diminishes as the frequency of the input signal is increased, which is an expected behavior of a low-pass filter. So here we have modeled the two circuits as linear constant coefficient differential equations. This gives the general form for these type of equations, where yn denotes the nth derivative of y of t with respect to t, and xm is the nth derivative of x of t with respect to t. N is also known as the order of the equation. A simplified version of these equations is shown here, where we have only the term x of t on the right-hand side without its derivatives. Once we have this equation, we can use it to solve for the output signal y of t, which we also call the response of the system. To summarize, in this lesson, we learned how to model electrical circuits mathematically as constant coefficient differential equations by going through two examples. For the series RC circuit, we got a first-order differential equation, and for the Sallen-Key circuit, we obtained a second-order differential equation. We then solved these equations using the Wolfram language and observed the output signal or the system response to sine waves with frequency omega. And we saw that the output response in both cases depends on the frequency of the input signal.